Uhum. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing? Doing good. Is everyone doing well with the new sunlight? Well, it's not dark right now, so with daylight, I didn't even know it was daylight savings this weekend. I thought I just slept in for an extra hour, but having trouble waking up the last couple of days. But at least the good thing is that it's still light at night. So if it wasn't for rain, but okay. So this is an off week. So we had our ANSYS activity 4 last Thursday. So this week is just going to be a couple lectures. So the topic for this week is more on meshing. So I call these lecture notes advanced meshing. I know we've been talking about meshing for a while, but meshing is really important, and it's probably one of the most important things that you'll do in FEA. So there's not really a big central theme to this week. It's really kind of just a lot of kind of separate kind of meshing topics on different things, kind of building upon different things that we've talked about over the last 4 weeks or so, but they're important, and because this is a graduate level course, it's important to go over these kind of more kind of niche, kind of advanced topics in meshing, because they do make a difference when you're doing finite elements at a high level. So that's kind of the plan for this week. Okay. So another thing, I know I'm a little bit behind in grading for this class. I know activity 3 is still out there. I haven't graded that one yet. I gave midterms for my undergrads last week, so I was kind of busy grading those, but all of those are done. So I'm going to be grading your guys' stuff tomorrow, I promise. Right? A few people have kind of asked me for feedback on the activities, just because I know you guys are starting to work on the midterm project. I'm going to give a little bit more careful feedback on activity 3 and activity 4, so that it can help you guys in doing the project as well. Okay. Okay. I think that's it for my announcements. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and start the topic for today. So the topic for today is called advanced meshing. Okay. So this topic here is really interesting. This is something that's kind of really unique to this particular class, just because this class is so focused on kind of the application with ANSYS. So I kind of teach an undergraduate version of this course. I teach another grad course, which is focused on the theory. And there's kind of some overlap in between those courses. But this is something that's kind of more unique to this. This is kind of when we start to make the transition to kind of talking about really kind of advanced kind of ANSYS stuff that's kind of unique for grad school. Okay. So just to introduce meshing, meshing, hopefully isn't anything that's new to you guys. Meshing is kind of the process of breaking apart your CAD model or breaking apart your geometry into simpler shapes that kind of facilitate finite element analysis. Because, like we've talked about over the weeks, is that, in order to solve the governing differential equations on these complex geometries, you need to be able to break up your geometry into these simpler shapes. That's basically kind of the crux of FEA analysis. Okay. But this process of, taking a geometry, breaking it up into simple shape it's not really the same thing as, taking a geometry and building it out of Legos. So that's kind of the analogy that I had for a long time. So, take your geometry and imagine if it were at Legoland or something like that. Meshing is a lot more complicated, and kind of the nature of the elements that you produce, whether they're skewed or not, the order of the elements, they all kind of play a really big impact on the results that you obtain. Now, I put the word dramatically in there, and I'm not saying that just to be dramatic. It really does make a big impact on your results. When you're using kind of a software like ANSYS, it's a little bit hard to kind of see these kind of dramatic differences, just because ANSYS does kind of a lot of really nice things under the hood that you don't really kind of realize it's happening. So ANSYS kind of does a lot of things to kind of fix a mesh that you may not notice. But if you use a software kind of outside of ANSYS, maybe a research software where the mesher is not so well developed as in ANSYS, you start to notice these differences quite a bit, and you can it really kind of makes a difference between, you know, a simulation that produces useful results with simulation that produces basically useless results. Okay. But of course, you know, if you are going to stick to ANSYS, you know, a lot of these things you don't worry about too much, but it's still useful to know about these things because it is, you know, sometimes it does kind of make a difference in places where ANSYS can't automatically kind of fix your mesh. Okay. Okay. And so, like I said, so the topic for this week are kind of more advanced topics with meshing that, you know, don't have a connecting thread between all of them, but they all kind of represent something that's kind of okay. Okay, so before we get into that, let's see. Start. Okay. So one thing that, you know, I've kind of hinted at over the last couple of weeks is this idea of, you know, high solution gradients. The first topic I have on there is about mesh quality and mesh skewness, but we kind of already discussed that already, so I kind of want to skip that. Okay. Okay. High solution gradient. So, you know, of course, this kind of depends on your finite element results, but whenever you have a situation where your finite element results undergo a big change or a big variation in a very short period of space, that's something that you probably want to look at from a meshing point of view. All right, that sentence is going to be a lot longer than I originally thought. But basically, you know, you're going to look for places where, you know, either the deformation is changing very rapidly or kind of more importantly, the stress is changing very rapidly. And these should be kind of areas that you kind of hone in on from your finite element results. Okay. Okay. Because what can happen in these areas that where the solution is changing rapidly, you know, maybe that's how it is. Maybe in reality, you know, you have a physical situation where the stress or the deformation is actually changing very rapidly in kind of a short period of space, right? And so just because you have high solution gradients doesn't mean that your solution is wrong. That may be just how the solution actually is. There's lots and lots of physical situations where this can occur. In fact, you know, it is something that occurs quite often in structural simulations. And so one example of this where, you know, you probably will observe this, you know, you probably observe this a lot in your projects as well, is you may see high stress concentrations near the locations of your fixed supports. Because a fixed support is actually quite an extreme constraint that you can put on a finite element simulation. Because what you're saying is that there's absolutely no deformation, no rotation, no nothing that can occur at that fixed support. Okay, but then if you're applying a heavy amount of load, you kind of have something that's kind of literally stuck between a rock and a hard place. So something that wants to deform a lot because it has a heavy load, but it can't because it's being constrained by the fixed constraint, okay, or fixed support. And so in those situations, the only thing that really can occur is you have a very high amount of stress within those regions. Okay? So you probably haven't seen that. You might have seen that in activity 3. You might see that a little bit in activity 4, depending on your mesh. But this is not all that uncommon. Right? And so when you see these, it's not a cause for concern to say, oh, my solution's wrong. The concern is more along the lines of, are we going to have enough elements, or are elements kind of refined enough to actually capture this variation accurately? That's the main question that you should kind of ask yourself whenever you see a region in your mesh or a region in your solution which has high gradients or has rapid change, okay? And the reason for this kind of all goes back to our discussion of element order. Because remember, the degree of variation that you can obtain in your result is limited by the shape functions of the element. Remember, the week, I think maybe a couple weeks ago, we talked about how every single element has a shape function which it uses to approximate the finite element solution within that element. Okay, and you're kind of limited to that amount of variation. Right? So remember, shape functions come in 2 flavors typically. So you have linear and quadratic. That means at most, you can only have quadratic variation within your element. So your solution can only change as quickly as a quadratic function can change. Okay, so if you plot out a quadratic function, I think you've all seen a quadratic function. So let's just look at f of x is equal to x squared, right? F of x is equal to x squared is just a simple parabola, right? And so with the parabola, a parabola does change fairly rapidly, right? And so if you kind of get, especially as you get further away from the origin, the slope of that parabola kind of increases more. Right? But in the realm of functions that can change rapidly, a quadratic isn't actually all that high power, right? Yeah. And so if you think of like a cubic function, cubic function can change a bit more rapidly than that. Color. Right, so you have a cubic function, x cubed, right? Just by the nature of being a higher order polynomial, it can change more rapidly than that, okay? Of course, you can go even further than this, and so there is a fourth order function. So there's more degrees of variation within that, within that realm of polynomials, right? So, I think this question was asked before. So, technically it is possible to have elements that are cubic or fourth order polynomial functions for their shape functions. It's just that a lot of times, in the way that my old colleague used to say, the juice is not worth the squeeze. And so kind of formulating the theory for a cubic element, you could do it. It's just you'd have to add a lot of different nodes in there to kind of make it work. And then the theory and the math and the programming just is not really worth it. Okay. But this is kind of an important limitation that you have to kind of remember is that, for a given function or for a given result, it can only change as quickly as the element order. Okay. So what happens if you have a situation where, your solution is changing much faster than a quadratic function? So because that is going to happen. And so you're going to have situations where you have, sometimes even exponential variation in something like the stress or the deformation. Okay. And so in these situations where you have maybe a particular region where your solution is changing very, very rapidly, the way to kind of fix this and make sure you capture that variation is to refine the mesh or to locally refine the mesh within that area. So what that's going to do is that it's going to make the elements within that area, within that region, much smaller than all of the surrounding regions. Okay. And this works really well because, remember the shape function only characterizes the variation within an element itself. It doesn't say anything about element to element kind of variation. Okay. And so if you were to just basically pack an area full of even more elements, then you're able to kind of capture that variation because, between elements, you can kind of make like if you think of it as kind of like a piecewise function, each function, each element can kind of adjust its shape function slightly to kind of capture that variation much, much better. Okay. So I'm going to give you an example with linear functions just because it's a little bit easier to visualize, but just know that this idea works for quadratic functions as well. Okay. Okay. And of course, it's going to be in 1D just because it's a lot easier to draw as well. So let's look at a piecewise linear function. And let's look at the situation for, for an increasing number of elements or an increasing number of kind of pieces that we can do. Okay. Okay. So let me draw a graph here. Do it all in one. And let's say that we have kind of an interesting behavior to our solution here. So let's say that maybe we have a period of fairly low variation, okay? So let's say our function kind of starts out very kind of slowly like this. Oh. And then near the end, we kind of have a very rapid kind of increase, just like that, okay? So this black line here kind of represents the true solution to the equation that we want to solve. Okay. And then in my in colors, what I'm going to do is I'm going to approximate this as best I can with a different number of elements. Okay. Okay, so let's look and see what happens if we try to approximate this function using a single element. Okay. Okay, so using a single element, we may get a function that looks like this. Okay. And so we have a single linear function here that tries to capture the entire thing, and you can see it doesn't do a great job. So you know, it tries to kind of pick a slope that's kind of the average, and we kind of end up with something like this. Okay. Okay. Let's see what happens when we increase the number of elements to 2, right? And so basically, we're going to be able to create a breakpoint right in the middle of this domain here. Right? And what you're going to say is that what you're going to see is that even with just 2 elements, we're going to get a much better capture of the results here. Okay. Okay, so with 2 elements here, let's put the breakpoint right here. Okay. So with 2 elements here, we can go from the origin to that point right there. So you can see from that first section there, we get a great match. Okay. And then for the second half, you know, maybe we look something like this. So you can see that by adding an additional element there, we can kind of recalibrate our line to kind of adjust it to, you know, the local kind of variation within that region. Okay. So this blue line here represents 2 elements. So even though, you know, we're still only limited to linear lines, you know, we just by adding additional mesh refinement there, we can, you know, we improve our approximation much more. Okay, let's just do one more, just because this, I think otherwise this graph is going to get very busy. So let's do 3 elements. Okay, so for 3 elements, let's put a dot here, and maybe a dot here. Okay. And so with 3 elements, you know, we have kind of 2 chances here to kind of recalibrate our slope. We end up with a much closer approximation to the true solution than either of the previous 2. Okay. And so, you know, even though individually, you know, an element doesn't have the right kind of function order to capture this variation, but together, you know, when you refine the mesh and you add more elements, piecewise, it can capture this much better. Okay, so this same idea kind of applies to regions in your finite element simulation where you have high gradients. And so if you refine the mesh in those areas, then you can kind of more properly kind of capture these differences. So when you refine, so that's essentially kind of what you're doing when you kind of refine your mesh. Okay. All right, any questions on this concept here? Okay, so you wanna be a little bit selective, right? Because remember, refining your mesh doesn't come for free, right? Because whenever you refine your mesh, you're adding some additional elements to your simulation, you're adding some additional costs, right? Kind of a unique barrier that you have in this class is that you kind of get closer to that limit of elements that you can possibly have in the educational version of ANSYS. And so you want to be selective with this. So, that's why, for this part, I want to be very careful and say this is a local refinement. This is not something that you're applying to the entire mesh, okay? And in fact, we've already actually done this. If you think back to activity one, right? In activity one, there was a part of that activity where I had you refine the mesh around the hole, right? And if you remember kind of what that simulation result looked like, we basically had a concentration of stress around the hole just because of how the plate was loaded at the time, right? And so by doing so, we were basically applying this effect right here, where we know that we're going to have a high variation of stress within that area, stress concentration. And so we refined our mesh in order to better capture that variation, right? So, this is definitely one thing you want to keep in mind as you guys are doing your project. And so you can look at areas where you have high concentrations or high variations of the solution and refine your mesh accordingly, okay? Because this is something that ANSYS actually won't do for you. Because ANSYS, like I said, ANSYS does a lot of things to kind of make sure your mesh is of good quality. Recalibrating your mesh according to your simulation results is not something that ANSYS does. And so I wanted to cover this first just because it's something that is, something that you kind of have to do kind of manually. So, okay. Okay. So what happens when you don't do this? And so what happens when you have a situation where your solution changes very rapidly, but you don't kind of refine the mesh to calibrate with it? Okay. So what can happen sometimes is I call it kind of like solution, well, I call it kind of splotchiness in the solution. That's kind of the best way that I can describe it is kind of a splotchy solution. But if you want kind of a more precise definition, this is a region where your solution kind of tends to flip-flop between solution values kind of, within the mesh. And you can kind of visually see this flip-flopping occur. Okay, so visually what this looks like looks like the following. And so, let's say you have a particular mesh in a particular area. So let's say that we have a simple triangular mesh here. And so a splotchy solution means that your solution is going to flip-flop between high values and low values within that kind of small region in space. Okay. So maybe for certain elements kind of on the top order, your solution has some kind of high value. So maybe the stress is fairly high. Okay. And then on the lower ones, if your solution is low. Okay. So visually, what this may look like is that you may have regions which are kind of red, like this. And then right next to it, you'll have regions that are kind of blue. Like this. This is kind of an extreme case, and so usually you're not going to see red, blue, red, blue, red, blue like this, but you may see like red, orange, orange, green, green, blue, and it kind of changes very rapidly in kind of short space. Okay. Ideally, what you should see is that when you have variations of high variations of the solution, the variation should have kind of a very smooth contour. So a very smooth variation from red down to blue. It shouldn't kind of go back and forth like this. So this is actually, one of the main things I actually look for. So, when I'm looking at your guys's simulation results for your projects, this is one of the things I look for. So if I see this in your solutions, then this tells me that, your mesh is not adequately refined. Okay. So if you do see this, what this tells you is that, you should probably refine your mesh within that area. Sometimes this can be hard to see in ANSYS because ANSYS kind of tries to hide it, honestly. So what ANSYS kind of does, it does some local averaging of kind of neighboring elements to kind of smooth out the solution, just because it looks appealing. A solution like this doesn't look that visually appealing. So sometimes you may have to turn it off. But actually, a good metric you can actually use in ANSYS is that you can do something you can check something what's called the structural error in the solution. Okay, so the structural error, what that basically shows you is that it shows you the strain energy field, but it does so in a very particular way. So it shows you the strain energy field between kind of the raw solution results minus the local average. Okay. So in the next answer, maybe not the next ANSYS activity. Well, we have to show you sometime before the project's due. So in the next ANSYS activity, we'll kind of talk about how to actually show this. Okay. Because ideally, if your mesh is well refined, whether ANSYS does this local averaging or not, it shouldn't show too much of a difference in the result, right? And so, if that local averaging is if that's kind of smoothing over these kind of splotchiness, then that usually shows up in the structural error kind of result here, right? And so if you want to kind of check kind of the quality of your mesh in terms of your solution, this is usually something that's good to check, because if you're just looking at the raw simulation results, your equivalent stress or deformation, unless you have a good eye for these things and you kind of know intuitively where to look, it can be kind of hard to spot some troublesome areas. But this feature here is kind of meant to help you kind of show you kind of where some problematic areas might be. Ideally, you want that structural error to be, well, low, right? We want low errors. Okay, any questions on this? Okay, and so to that end, there's kind of a general, I would say, kind of methodology or general kind of process to follow when you're making your mesh, right? Usually you don't want to be satisfied with just the first mesh that you produce, right? Even if you've been doing it for a long time like me, I still follow this process to produce a mesh that I'm comfortable with in terms of accuracy of the results. Okay. And you're going to do some of this anyway when you're producing something like a mesh convergence test. And so, you might as well look for a few more things as you're doing your mesh convergence test. Okay. Okay, step one. Step one is just generate your initial mesh. You don't have to be too careful with that initial mesh, and so you don't have to add any local refinement. You can, of course, if you kind of know ahead of time, where some problematic areas might be, where your stress is gonna kind of concentrate. You can add refinement, but usually for your initial mesh, you just need a mesh with a pulse to work with. Okay, step two, apply your boundary conditions. Right, so those boundary conditions are going to stay fixed, right? So you don't have to change them. Step three is to run your initial simulation. Right. So a very basic simulation with kind of a very basic mesh, right? So that at least all your boundary conditions are there. Okay. And then after you run your first simulation, that's when you start to analyze and look at your results. Okay, so step four here is to look at your simulation results and identify areas where you have, high solution gradients, or maybe areas where your structural error are high. Step five, once you've kind of identified those areas, so those will be areas where you can refine your mesh and then improve your solution, right? So step five is to actually refine your mesh in those areas. By the way, refining your mesh doesn't always mean to make the elements smaller, although 90% of the time that's kind of what it means. But maybe you try a different element shape, maybe you try a different meshing scheme, and so we're going to talk about a few other meshing settings kind of later today. But basically, the idea is to improve the mesh in that area in some way. But 90% of the time, realistically, you're going to make the elements there small. That's the solution to most meshing problems, to be honest. Okay, once you refine your mesh, go ahead and run your simulation again. Okay. Right, after you run the simulation again, you'll be able to see how much those areas improved. And so if you see a big difference in the solution, those areas, that means your techniques or the settings that you provided did lead to an improvement. Okay. You should hopefully see some improvement. And so, you should see maybe a change in the solution value, maybe the solution gets smoother, the structural errors go down. That's kind of a good way to kind of see, right? And so you should see some improvement, right? And then step 8 is just to repeat this process again. So you're going to go back to step 4. and then just kind of keep repeating this and keep refining your mesh, okay? You want to do this until you don't see any improvement on your simulation results anymore. All right, so this process here is it's a good process to follow for basically any finite element simulation that you're going to do. Okay. And if you're kind of if you kind of connect this to kind of what we talked about a couple of weeks ago, steps 4 through 8, that's essentially what you're going to be doing in your mesh convergence test anyway. Because in your mesh convergence test, you basically want to illustrate that the changes to your mesh, you basically optimize your mesh in order to reach convergence on your solution. Okay. So this whole process is just kind of another way to talk about mesh convergence. But instead of kind of just blindly and kind of globally making the mesh smaller, you're doing it in a little bit more of an intelligent way and refining the mesh and really in only the area that you need. Right. So this process of improving your mesh, this should be part of any simulation that you do. Just that in this way, you're doing it a little bit more, you're being a little bit more selective and try to maximize that outcome. Okay. Or excuse me, maximize that solution. Maximize solution actually by minimizing the. Now, of course, as your simulations get more and more expensive, so this process, for the simulations that we're doing in this class is very reasonable because the simulations that you're going to be doing, they usually don't take more than just, maybe 10 seconds. And so you can kind of iterate on this. You can do this even, maybe a dozen times and it's not that unreasonable. But of course, as your simulations get more expensive, if you're doing kind of, practical simulations with millions of elements, this process, of course, is going to take longer. So of course that places a limitation on how many times you can iterate. But the idea is that, by getting enough practice on kind of these lower cost simulations, you start to build some intuition and you start to be a little bit more intelligent in terms of where you want to add your refinements. And this is true, if you're doing a heat transfer fluid mechanics simulation. Okay, any questions on this? Okay, good. All right, so there is one caveat to this, right, that you want to be careful about. And this is something that's, not unique to structures, but, I think it's kind of easiest to kind of illustrate with a structural FEA. And that is with stress singularity or solution singularity. Okay. So, the above discussion of kind of this whole thing with improving your mesh, it's kind of built on this assumption that as you make the elements smaller, you're going to get a better quality solution. You're going to approximate the solution much better than if you did with the bigger elements. This is generally going to be true, 99% of the time. Okay. But there are situations where if you actually refine your mesh, it's actually going to make your solution worse. And it's important to kind of recognize when these situations are occurring, so you can go in and fix it. Right? It's usually very specific situations that cause this to occur, but you know it is important to know. Okay, so the example I'm going to give you is it's kind of very specific to structures. Hopefully, it's something that you've kind of seen before in your structural mechanics class, solid mechanics, strength of material, and you're going to see that FEA actually kind of makes this problem, you know, better. Okay. Okay, so the example that I'm going to give here is, is the example of a stress concentration at a sharp 90-degree corner. I guess it doesn't have to be a 90-degree corner. It's just one where you have a very, very sharp corner. I'll say 90 degrees just for drawing simplicity. Okay, so let's say that you have a structure that looks something like this. Let's say that we have kind of a concave internal corner within the structure itself. I should maybe add to this. So it has to be not just a 90-degree corner, but a concave. But basically, the structure has to kind of form kind of a concave, area like this. Okay. So very simple geometry, right? So you can imagine a geometry might have a corner like this, right? So if you actually solve the equations of elasticity, for this, for this structure here, and you solve it analytically, so you solve it with pencil and paper, elasticity theory basically says that whenever you have a sharp concave corner like this, the computed structural stress is actually infinity at this location. And so generally, if you've done any kind of structural design before, you know to kind of avoid sharp corners, just because those are areas where your structure might fail. That's also why crack formation and crack propagation is such an important area of study in structure, because a crack is nothing more than just a very concentrated sharp corner where stress can kind of really concentrate. So this has important implications for FEA. Okay. In actuality, if you were to try to run a simulation like this in FEA, you're probably not going to get infinite stress, because what happens when you apply a mesh onto this corner, the mesh is kind of naturally going to provide a nice kind of fillet to that corner. Because it's very difficult to actually get a mesh that fits that corner perfectly. Even if you use kind of hexahedral elements or quadrilateral elements, it's usually going to be the case where you're going to have a little bit of a fillet there because the elements are not going to fit that corner exactly. And so if we kind of just kind of show that same corner here. Okay. And then in green right here, I'm going to show you kind of what the mesh might look like in that area. So let's say that we have triangular elements here. So maybe your mesh looks something like this. So kind of once you get into the region of this corner right here, what's going to happen is that as the mesh tries to kind of mesh that corner, tries to get around it, it's going to provide kind of a natural kind of fillet within that corner itself. And so, you can see here, it's a little bit kind of hard to see. But you can see here that through the elements there, that corner is kind of softened a little bit. It's not as sharp as it was before. Mesh. So the mesh can't capture that corner exactly, but it actually kind of smooths out that corner, which is actually kind of good because, when you actually run the simulation, you don't actually get infinite stress there because it's not exactly 100% at a very sharp angle. You do get a very high stress, but at least it's not infinite. So you're kind of saved a little bit just by the fact that your mesh is kind of an imperfect kind of representation of your geometry. Right? But that kind of gives us a little bit of a paradox here, because if you were a little bit naive, you might look at that and say, like, oh my gosh, I have such a high stress there. If I'm following the same methodology that we had talked about, I should refine my mesh in this area in order to improve my solution result. But that's kind of usually what your first instinct is that if you have a high solution gradient, a high concentration of stress, that should tell you that you need to refine within that area in order to get more accurate results. Okay. But in this situation, in this kind of very unique kind of situation, refining your mesh actually makes your situation worse. Because as you refine your mesh, the mesh is going to get better and better at kind of approximating that sharp corner. And then you get closer and closer to this idea of of this concept of infinite stress because you're solving those elasticity equations. And so you kind of enter this kind of endless loop of making the situation worse. And so, you do your initial mesh, you see a high stress concentration, you refine your mesh, you see your stress shoot up even more, you refine your mesh even more, you see the stress shoot up even more, and you keep doing this until you have a bajillion elements and your stress is also a bajillion. So you think that something's gone terribly wrong, because it has gone terribly wrong. Okay. And so you want to look out for these situations. And so, usually if you're working with a CAD model that's kind of meant for production at some point, you're probably not going to get these sharp corners because, if you've done any kind of manufacturing before, making sharp corners is kind of a pain in the ass. And so probably you're not going to have these to that extent, but that's definitely something to be careful about. Okay. And so if you have a situation where, it may not be a sharp, it may not be an obvious sharp corner, but if you have a situation where you keep refining your mesh and your stress keeps shooting up, you may have a situation like this. you want to be careful of those situations. So as you're refining your mesh, if you kind of observe a situation where your stress kind of keeps going up and it keeps going up unbounded, you might have a situation where you have a solution singularity or stress singularity, more so than your solution is just not accurate. Right? And so what do you do in these situations if you have a solution where you have a singularity? Probably what you're going to need to do is you need to go back and actually modify your geometry and make it so that you don't get a singularity in that area. Okay. A lot of times it should be pretty obvious, and for structures, most of the time it comes from sharp corners. And so if you see kind of a sharp corner and stress starting to concentrate in a very particular region, you probably want to go back and kind of smooth out that area, maybe add a fillet, or maybe add a round to that area, or maybe reconfigure the geometry so it's not so sharp. And so a lot of times it is kind of fairly obvious, but it is something to kind of look out for. And if you have a situation where this is occurring, then definitely something to say to kind of take a pause, take a step back and stop refining and kind of see exactly what's going on. Okay. Any questions on this? Okay. All right. So the last thing I want to go over today is kind of two very important settings within ANSYS, called patch conforming versus patch independent. So this topic is kind of a little bit separate from kind of everything that we've been discussing. And so, like I said, this whole section of advanced meshing is kind of a mishmash of different kind of topics in meshing, but this is kind of an important. You may have noticed this already. And so if you think back to your ANSYS activities and you think back to the method object that we apply on our mesh sometimes, you should see that there's a part of that meshing method is whether you want a patch conforming or patch independent method, right? It's right up there with the element shape and the element orders, just that we haven't modified this up until this. Okay. So patch conforming and patch independent, these are kind of two different meshing schemes, and they kind of revolve around how ANSYS actually produces your mesh. Because in reality, there's a lot of different strategies that can be employed to produce a mesh. In fact, there's a whole field of research kind of in that, in that field of kind of mesh generation. What's the kind of best way to kind of do this? ANSYS kind of gives you these two methods here. But just know that there's kind of a lot more out there. But these two kind of cover most of the cases that you're going to see on a practical basis. Okay. Okay, so let's go over patch conforming first, because that's the default. So that's the one that you've all been using up until this point. And so if you don't change anything, you're going to be using a patch conforming method. So the patch conforming method, I like to kind of describe it as kind of outside in. And so the way the patch conforming method works is that it takes your geometry, right? And so remember, this is the process of kind of actually producing the mesh itself. And so the way patch conforming works is that it takes your geometry and it takes the shell, or it takes the outside of the geometry, and produces a surface mesh on that outside shell first. Basically, it takes your geometry and it extracts just the shell that wraps around the outside, so a very thin shell, and basically produces shell elements on that geometry. Okay, so you have basically kind of a surface mesh or a two-dimensional mesh, or I should say a mesh with two-dimensional elements that just covers the outside of your geometry first. And so at this point, once the surface mesh is created, the mesh is then grown interiorly. So basically, tetrahedrons or hexahedrons are then kind of created and kind of grown towards the inside up until the full volume mesh, or the entire volume of your mesh is done. Right, so your mesh is literally grown from the outside and going in. That's why I call it kind of the outside in method. Okay. So the patch conforming method, it has a number of benefits. That's why it's kind of the default. Okay. And so with the patch conforming method, because the surface mesh is kind of produced first, the patch conforming method does probably the best job at kind of respecting the overall dimensions and overall kind of features of your original CAD geometry. And so for situations where it's important for you to kind of emulate those kind of complex features on your CAD model, patch conforming method is the best to do that. Okay, so it's not going to defeature, it's not going to smooth over any any features unless it's a really tiny feature. Okay. So if geometrical fidelity is important to you, then patch conforming is good. The downside the patch conforming method is that it's more prone to failure, and so this kind of idea of kind of growing your mesh interiorly is not super stable, and so there will be situations where your mesh it'll try to produce elements that kind of overlap with each other, which will cause the mesh to fail. And the downside is that when the mesh fails, you know, you probably everyone's experienced this in the class at some point. The ANSYS doesn't actually give you a very helpful message to tell you that it's failed. It just says mesh failed. So, you know, that's very frustrating sometimes, okay? The patch conforming method, even for cases where it works, it's also more likely to produce skewed elements. Because the way this kind of growth, this growth method works is that it, you know, each surface is kind of grown independently. And so they're not really communicating with each other super well. And so oftentimes when you grow a mesh inwardly like this from several different points in the geometry, you know, you're going to have a lot of kind of weird nooks and crannies and a lot of weird crevices in the model, which, you know, sometimes the mesh can fill, right? So it can probably fill those with an element or two, but you may end up with very kind of skewed elements as a result. And just like we talked about, you know, maybe probably about a month ago, you know, you want to avoid having skewed elements in your mesh, right? A few skewed elements is usually not that bad. You're usually going to have those no matter what. But you don't want to have too many of those. And if you have a skewed element in a particularly kind of problematic area, and so let's say you have a highly skewed element in a region where you have stress concentration, that's going to throw your solution off quite a bit. And so if you use the patch conforming method, you know, you're much more likely to have skewed elements like this. And for those of you that, you know, for the past two activities, you've checked the mesh quality, you've seen that, you know, no matter what you do with the mesh, you're going to get some skewed elements no matter what you do. And part of that is a consequence of this patch conforming method that we're okay. All right, so patch conforming, it's great when you want geometric fidelity, when you want your mesh to conform to your geometry, but sometimes it can produce, you know, some issues with the mesh. Any questions on patch conforming method? Okay, so last thing we're going to cover today is the opposite of this, which is called the patch independent. And once again, you know, these settings are, you can access them from a method object within the mesh itself. So the same way that we change the shape of the elements and the order of the elements, you can change the setting here as well. Okay. So patch independent is kind of opposite. And so patch independent, I call kind of the inside out method. So in the patch independent method, your mesh is grown from the interior of your geometry and grown out towards the boundaries. And so the idea is that, you know, a seed is usually placed kind of somewhere within your model or maybe at multiple points within your model, and mesh elements are grown from that seed. And so during this method of element growth, because you're kind of starting from the interior, it's a lot easier for the algorithm to prioritize kind of high quality elements. And so nicely formed tetrahedrons or hexahedrons. So that's good, right? And so if you have high quality elements, that's generally kind of a good thing. Okay. And the way this method stops is that, once the growth kind of exceeds past the boundaries of your geometry, then what happens then is that the elements are then kind of, they're kind of cut off right there. So you basically kind of project the element node back onto your element boundary so that you kind of maintain that geometric, the overall shape of your CAD geometry. So that way, you're able to kind of maintain your element boundaries. Okay. And so kind of the pros and cons of patch independent are kind of opposite that of the patch conform. Okay. So the pros is that the patch independent method is less prone to failure. And so it's, because the algorithm kind of works from the inside out, you're much less likely to get overlapping elements, especially if you just have a single seed. It also produces higher quality meshes. But of course, the downside is that, because the boundaries or because the exterior of your geometry is not really accounted for until the end, you may have situations where your mesh doesn't perfectly conform to your geometry, especially if you have kind of complex surface features on your geometry. And so if you have a geometry with, a very complex surface, very complex features, patch independent may not capture those all that well. But like we're going to talk about on Thursday, if you do have a geometry with a lot of complex surface features, you may want to think about not having it. So you may want to think about, reforming your CAD geometry, simplifying the surface, simplifying these kind of complex things. And, these complex things are usually they're not always kind of superfluous. And so, even things like threads on a screw or threads on a bolt, that can be hell for a mesh to try to mesh as well. So next time when we come on Thursday, we're going to continue this discussion. We'll talk about defeaturing, maybe kind of suppressing some of these complex features to try to get as high a quality mesh as possible. Okay. All right. So thank you guys for coming today. Hope you guys have a good rest of your evening, and I will see you all on Thursday. Yeah, sure. Yeah, that's fine. Yeah, that's kind of the exact conversation. Yeah, so one way that you could fix that is that I think the original setup that the big support on one end and this weight on the other. So it actually kind of puts too much stress on this one. Actually, if you think the big support on both, then it kind of distributes the stress a little bit more. Oh, nice. Yeah, that was much better.
Right.
Yes, no.
Let's do one more.
If you refine it.
Yeah. It's hard.
Yes, the other was all.
You didn't
You guys-
have it? Okay. Hey,
What's going on, Nick?
The first one was.